Okay, so here we go. We're looking at number 32 from the review. So we're going to hit this thing. So here's our ground. Here's where we're teeing off right there. And we're going to strike this ball so that it leaves here at a 20-degree angle. And its initial velocity is 180 feet per second. So we can think of that velocity vector. So it is truly a vector. And so we have that angle, we have that magnitude. And so what we want to do then is figure out when is it going to hit the ground and where is it going to hit the ground, how far has it gone. So what we do is we think of this vector and we want to break it into, first of all, its horizontal and vertical components. So if this is 20 degrees, then we're going to have this horizontal piece of the vector, and we're also going to have that vertical piece of that vector. So that is our velocity vector is going to be, well, in the x direction, that's going to be the magnitude times the cosine of 20 degrees. Is that okay? Kind of. Well, we can do it, we can know that in general, x is going to be r cosine theta, and y is going to be r sine theta. We okay with that?
Yeah.
Okay, if not, we can draw the right triangle and come up with it. So that's perfectly fine. I mean, that's not a lack in your character, a fault in your character if you don't remember it off the top of your head. So you can recreate it. That's the main thing. So then we're going to get 180 times the cosine of 20 degrees, and we're going to get 180 times the sine of 20 degrees. That's going to be the vertical component of that vector. So now we're going to kind of idealize this a little bit because we don't know any physics, and we're not really interested in learning physics. Did I say that? So we're going to imagine, we're going to ignore any air resistance there might be. You know, this is going to be kind of a perfect situation here, an idealized situation. So when we strike that ball, it's going to go horizontally as far as we know forever. I mean, it's not going to have anything that's slowing it down or keeping it from just continuing on that path. So our x of t is going to be 180 cosine of 20 degrees. However much of that initial velocity vector that we hit that thing with, it's going to keep going that way in perpetuity as time goes on. Nothing will ever slow it down or stop it horizontally. But now vertically, we still live on planet Earth, and so we still have this whole gravity thing going on. So this thing is going up with this initial velocity, but gravity is pushing it down. Okay, so we remember that, who could forget, that acceleration due to gravity in English measure, because we're in feet, is, on physics students, negative 32. And we also know that acceleration is the second derivative of position. Why do we call position S? It's a physics guy made that one up. You clearly don't know how to spell position. It doesn't start with S, but that's what we got. So we integrate both sides and get with respect to t. And so we get a negative 32t plus c is s prime, otherwise known as the velocity. Okay, and we know that in our case, at time 0, that initial velocity is, no, it's 180.
Okay. Yeah.
Okay, so we get that, but actually the velocity vertically is going to be 180 times sine 20. Okay, so we got now at time 0, so v of 0 is equal to that 180 sine 20 degrees. Okay, so that becomes our c. So now our velocity, which we know is the first derivative of position, is going to be negative 32t plus 180 sine of 20, period, end of story, for velocity. Okay? So we integrate again. I'll do the left side. Integral of s prime is s. Now, who could forget? Integral of negative 32t with respect to t is going to be negative 16t squared. Integral of a constant, even though it's a weird constant, with respect to t is going to be that weird constant times t. And we get a third constant. It's the only constant now. Constant of integration. And s of 0, our position at time 0, because we are hitting this thing off the ground, our t has negligible height, is going to be 0. Gotcha? You get out and golf a little more. Just kidding.
It's really hard to find a left-handed cloud.
I know. I'm left-handed too. So we plug in 0, c is 0. So what we get is that our position vertically, if we're just looking how far down does it go, this is it. So that is going to be our y of t is going to be negative 16t squared plus 180 sine of 20 degrees times t. Okay, that's the hard part. Now, we want to know, when does this thing hit the ground? Well, our horizontal component says this thing is going to go on and on and on and on, but the vertical component doesn't say that. Gravity is going to push it down into the ground, and that's when we're interested. When does that hit the ground? So what we want to know is, when is this height equal to 0? That make sense? That's when it's going to hit the ground. So we'll take negative 16t squared plus 180 sine 20 degrees times t and set that equal to 0. So we can factor out a t. And so when t is 0, it's going to be on the ground, but we knew that because that's where it was when we hit it. That's time 0. Okay. And then the other question is, when is this 0? And we can do that. So if we're going to get 16, if I add that to the other side, like so. Okay. And this we need to keep with as much accuracy as we can. That first, this will answer the question, when does it hit the ground? And so this we can write to 3 decimal places. Does anybody happen to know what it is?
3.848.
848 seconds.
If the answer to you, sorry.
Okay, if I answer, did anybody else get that?
I got that.
Okay. That makes me feel better. So that's when it's going to hit the ground. And so then we want to know, where does it hit the ground? So that means we're looking now for, where is that horizontal distance when it hits the ground? So when t is this, and we'll use all the decimal places of accuracy, what is its horizontal distance? And so that value of t, we'll plug in there, and that will give us how many yards down the fairway that thing hit. Okay.
Part A was to draw a graph. Can you briefly go over how to do that?
Yeah, let's do that. So now this I have not had great success with in the past. So I'm going to try to turn the camera so that it can see the TV screen where I'm going to put my calculator. But if this thing turns off, which it has been doing, I'm going to try to restart it. So I'm going to try to pay attention to that. So me and technology have had our struggle. Like I said, my apologies to the people, how did I do that are trying to watch this. Oh, that didn't go well. How did that happen? I have no idea if that's working. What did that do? Well, be glad you're here in person. apparently it's still running. Oh, good, we got all that. That's important. Okay, so that is my actual calculator screen. Let me see if it shows. Ah, there we go. Okay, so we're gonna go to, we have to go to mode, and we want to be in degrees because we're talking sines and cosines of degrees. And we want to go to parametric. So we're gonna highlight the PAR for parametric. Whoa.
Starting off a function before.
Oh my, this is uncharted territory here.
Yes.
We okay? This is gonna be fun because now when you hit y equals, oh my goodness, get all kinds of, well, mine has all kinds of crazy stuff on it. Look at all that. Somebody's been playing on my calculator. Wait till I get a hold of that person. Okay, let me get all that other stuff. Well, oh, look at that. It goes on and on and on. Jeez. I think somebody would have something to do with their spare time. Okay, any more? Oh, that's good. That's all there is. Okay, so let's try to get back up to the beginning of this stack. Okay, so we are going to put for x1 of t, we're going to put in this 180 cosine 20 times t. Or what I'm going to just do is 180t. I think that's, so I don't have to deal with the, when you hit the xt theta button in parametric mode, it shows up as a t. And then I'm going to go, we're horizontal, so that's cosine of 20, and close the parentheses. That should work. Okay, and I'm going to drop down and do the negative 16t squared plus, I'm going to call it 180t sine of 20, and I think that's good to go. And now we got to figure out what our window is, and I don't remember what, so we know we want to go down a long way. I don't remember what I did that on, so I'm going to guess here. So let's go to window. Well, we know we want to go to at least 3.848 seconds. So I'm going to call that 4 is close enough. So I'm going to go 4 seconds down. Now the t-step we want to be somewhere in the neighborhood of 0.1. And the x-min, I'm going to say 0, and then x-max, it's going to be a long way down, I think. What do we know what the answer is actually? 400 or something? What is it? 650? Ooh, there was a stiff wind behind that one. You don't have any real golfers here that know how unlikely that is, right? It's a downhill course. Very hard. So when it hit, it rolled. No, I'm just kidding. So let's go 650. Let's go 700. And let's make our tick mark something like 100. We don't want to have a fat x-axis. Y-min, we can leave that as -1. And Y-max, I don't know, was it like 80 or something? Or big? Let's go 100. Let's be bold. We'll choose tick marks there to be, say, 50. Okay. Now, you ready for this? This is where it gets exciting. I sure hope this works. Oh, bam. That's kind of cool, wasn't it? Question?
Just to clarify, when you want us to graph the parametric equations, we can use our calculator?
Yes. Yeah. But you're going to have to, now, when you do, because the one you were asking earlier, what number was that? The one that makes the figure 8 or something?
That was
Yeah, that one's
31.
easy if you can use your calculator.
Okay, yeah, I want you to use your calculator, but you still have to make sure you're labeling your x and y axis, so I know what that is. You have to show the orientation by putting the arrows.
How do you find that?
Then you have to watch it when you graph it.
Oh.
So you will see it, and I don't remember how it went, but it's going to do something like that.
Yeah.
But if it did it the way I did, you would write arrows to show, that's called the orientation.
Yep.
So it has a direction in a parametric, or a parametric equation has a direction, and that's of interest. So you show it by putting the arrows on where it goes.
Is there any way to figure it out without watching it, how it comes on?
I mean, you could, but it'd be more, I would say just watch it. Is the way to go. And yeah, you could plot points. You can start 0 for t, 1 for t, 2 for t, see which way you're going. I don't know if you really want to do that. I would just watch it. Okay? Any other, that's good. We got to blaze on. So now, okay, can I not turn off the camera and still get back to apologizing for those 3 people at home that are watching this, that are in the B cohort. You're going to be getting seasick.
How many people do you have?
Sorry about that. Why? It has never done that before. Should turn it off when I'm doing that, but I'm not. Okay. Sort of centered, more or less. Okay. Okay.
We're there. Okay.
It was kind of fun, except for the bit where we have to do more. But like, just talking about the idea, like, that was something that.
Okay. So let's talk about vector projections. So this is, I think one of the tougher things that we do.
Oh, dang. You mean the rest of it wasn't?
That was a warm-up.
A lot of.
So we know that we talk about vectors and their vertical and horizontal components. So essentially what we're doing with that is we're taking some vector and we're saying, you know, how much of it goes in the direction of the x-axis and how much of it goes in the direction of the y-axis. But truly there's not really anything special about the x and y-axis other than the fact that they're perpendicular and they're nice because we think of that as a reference point. But it would make perfect sense to take a vector and say how much of it goes not in the direction of x and y, but maybe in the direction of some other vector and a vector perpendicular to that. That is, we could resolve this vector into how much of it is going in whatever direction we're interested in, and how much of it is, in a sense, kind of like wasted. It's going perpendicular to that.
I have a question on this. So when we're doing this, it has to be two vectors that are perpendicular?
Yes,
Okay.
yes. The vectors have to be perpendicular for this to work. Okay, or more interesting, or more typically what happens is we are saying that, you know, maybe what we want to do is we have some vector and we want to know how much of that is going in the direction of this vector. That's what we mean by the vector projection. So this doesn't have to be the x-axis. This could be just any old vector. So this I'm going to call vector u. And we can project vector u onto vector v. Now it might be that v is really long like this, or it could be, I'm going to try to redraw v the same, which never works, but or u the same. But we might have a short v also. So the length of v is going to matter a little bit here. So the idea in the vector projection is if we drop that perpendicular, then this much of it right here is the projection of vector u onto v. Now here, vector v is really big, and so we get part of that vector. Here, v is short, but that projection would still go out to where that perpendicular falls. Okay? So it's how much of that vector u is acting in the direction of v. And the direction of v, or the length or magnitude of v, is really irrelevant. That's not what we care about. So whether v is a really long vector or v is a really short vector, somehow we don't want that to impact what our choice of the projection vector is. Okay, and we'll talk about how that works. So this green vector here is known as the projection of vector u onto v. Let me make sure I wrote that the right way. The projection, don't write that down yet. It's the projection of u onto, yep, that's right. So projection of u onto v, we write there. Just u comes here and the v is the one we're projecting onto. Okay? Okay. Cool. So I want to find that right away, go on talk. So if that's our projection vector, then we can find, because the other part is sometimes we'll be asked, sometimes that's all we're interested in, is what is that projection vector, or maybe just what's the magnitude of that, how much of that force that we're going this way is acting in that direction. So sometimes we might only be interested in the magnitude of that projection vector. Still other times we might want to, like we talked about, write this vector u as the sum of two perpendicular vectors, one of which is that projection vector. The other one would be this vector right here. So can we write, if this is our projection vector, if I call that vector w, then there are times where we want to be able to express u as the sum of that projection vector of u onto v, the projection of u onto v, which is a vector, plus that vector w where these are perpendicular. And it turns out that's not really hard to do. The hard part is finding the projection vector. If we can find this, and we already knew that because that was given to us, we can solve for the w just by subtracting that over. And so we'll find that w by taking our starting vector minus that projection of u onto v. Is that okay? Okay. So how do we find that projection vector? You okay with that? Can I erase that? I'm going to start over fresh here. So we can consider either of these. We'll talk about that length of v in a minute. I'm going to draw the picture more like this because it's just a little less cluttered that way, but it doesn't really matter. So let's see, I started with vector u. That's our vector u, and I think that I make v yellow, I don't even remember. So there's our vector v, and so our question is, how do we find the projection of u onto v? All right, well, we're going to drop that perpendicular down here. And so this vector right here is our projection vector. That is the projection visually of u onto v. And to just simplify things a little bit, I'm going to say the magnitude, because I'm going to find that first, the magnitude of the projection vector of u onto v, I'm just going to call w so I don't have to keep writing all of that, magnitude of projection vector of u onto v. So we can see that here's our angle theta between those two vectors. And we know that the cosine of that angle two different ways. We know it from dot products, and we also know it from SOHCAHTOA. And so we're going to find it in each of those and set them equal to each other and see what that gives us. Because we'll get an expression for this w, which is that magnitude of the projection vector of u onto v. Once we can get an idea, an expression for what that's equal to, then we'll talk about how we make it a vector in the direction of v. That'll come later. Is that okay? So we know that the cosine of theta is from SOHCAHTOA. We know that that's going to be the adjacent side, which I'm going to call w, over the hypotenuse. What's a good name for the hypotenuse using vector terminology? Yeah, absolute value of v, or magnitude of v, of u rather. So this is going to be the magnitude of u. Is that okay? So that's one way we get at the cosine of theta. We can also get the cosine of theta from what we talked about with vectors, using the dot product. Do you remember that one? Because you need to know this one. It's going to be u dot v over magnitude u, magnitude v. Okay? Well, that's the same cosine theta. So now we can set those equal to each other. So this w that we're trying to find over the magnitude of u is u dotted with V over magnitude U, magnitude V. So this magnitude of the projection vector, which we call W, if we multiply that magnitude of U to the other side, just kind of just cancel that. Right? Multiply by the magnitude of U on both sides, and they'll cancel. So we're getting this W, which is that magnitude of the projection vector of U onto V is going to be U dotted with V over the magnitude of V. Now, I think it's worth pausing here a moment just to think about what this is really saying. So we're saying, you know, the question at the start of this was how much of U is going in the direction of V. And so in some sense, it's that dot product, right? U dotted with V is going to give us an idea of how much is going in that direction. Because remember, if U dot V is 0, what does that tell us? They're perpendicular. And if they're perpendicular, how much of this vector that we're trying to project onto this one, how much of that vector is going in that direction? 0, right? And on the other hand, if they were totally collinear, you know, if U was going completely in the direction of V, then U dot V would be the magnitude of U squared, right? So all of it would be going in that direction. And wherever else we are, we get some fraction of that. So the dot product holds in it how much of vector U is going in V's direction, but it's affected also by the length or magnitude of V, right? Because if V is really long, that's going to be a bigger dot product. But if V was really short, that would make for a smaller dot product, but it wouldn't change how much of U is going in that direction. So to kind of standardize it, you have to divide out the magnitude of V.
So is that as a actual number as a length, or is it a proportion of the length of V?
Yeah, well, it's a number
Okay.
that represents how much of this vector is going in the direction of V. And this is unaffected by what V's actual length is. So this number, whether V is really big, like I've shown here,
Okay.
or if V is really small there, because I'm dividing out the magnitude, will kind of be standardized.
Okay.
So it's unaffected now by dividing by the magnitude of V. It's unaffected by how long V actually is. So it takes away any distortion from there. So that's how much of it we want in the direction of V. Oh boy, Gracie, we're struggling today. More caffeine at lunch, kiddo. More, the answer to all of life's problems. So now we want to make this a vector in the direction of V with this length or magnitude. So what we really want is a vector in V's direction of length 1 that we can multiply this by. So this will hold the magnitude because we multiply this number times a vector of length 1, then its magnitude becomes this number. You with me there? So here's a vector of length. Let me try to make it as simple as I can. Do this off the top of my head. There's a vector of length 1. Its magnitude is 1. If I multiply that by a number, now its magnitude is going to be 5, right? So I'm going to take a vector of length 1 in V's direction and multiply it by this. How do I get a vector in the direction of V of length 1? How do I find a unit vector? That's what I mean by a vector of length 1. In the direction of vector V. Search. It's in there somewhere. You take V and divide it by its magnitude. Make sense? Yes, no? Want an example of that?
Yeah.
So here's a vector. I'm going to make one up. K for Kieran. This is a vector 3, 4. Okay, not a unit vector. What is its length?
5.
Yeah, square root of 9 plus 16 is 5. Take k divided by the magnitude of k, it's going to be 3/5, 4/5. Still in that same direction. Right? Can you tell it's still pointing in the same direction? But now its magnitude, its length, is 1, because square that, 9/25 plus 16/25 is 25/25, is length 1. That's a unit vector in the direction of k. Now, if I want that to be a vector, a length whatever I want, suppose I want it to be 10, a length 10, I would just take 10 times that unit vector. And I've created a vector in this direction with that length. Okay, that's what we're doing here. This is now going to be our vector of length 1, a unit vector in the direction of v, and I'm going to multiply it by that so it has that length. And so our projection of u onto v is going to be this mess, u dotted with v over magnitude of v times our unit vector v over magnitude v. It looks awful. What a mess. There it is. I think of it this way because this is the way I remember where it came from. But, I mean, it is kind of nice when you multiply these two, you get the magnitude of v squared. So you will often, probably usually, see it written as u dotted with v over the magnitude of v squared times vector v. So this is that number, scalar, times the vector v. Okay? Now, what's really cool, what if v is a unit vector? Oh, what if vector v is a unit vector? Wow. Now, look at what our projection becomes. The length of that projection of u onto v, if v is a unit vector, is just u dot v. Ah, so cool. And then our projection vector, if v is a unit vector, is just u dot v times our unit vector v. If only life was always so good. All right, I think we better do an example. Okay, so let's say find the vector projection of u, which is the vector 6, 2, onto v, which is the vector 5, -5. Then, so that's our first task. Then, write u as the sum, write u as the sum of two orthogonal vectors. Orthogonal vectors, one of which is the projection of u onto v. Oh, I might have wanted to keep that. Oh well, you got it in your notes. Yes.
Can we go to the bulletin board on this?
Do you want to try this on the board? If you want, we'll do it together. You can go ahead and go to the board. I'll do it with you. I like that kind of courage, adventurism. It just helps me learn. I know. I totally agree. I had one year, just different classes are different things. I had one year where we had a BC class. They wanted to go to the board for everything. I mean, I would hardly get into a lesson, and they were up at the board doing it, and they would collaborate, and I mean, it was just the way they learned. It was great. I mean, not every group is, and other groups I've had, I can't get them to the boards. It's like, they don't want to. Okay, so should we draw a picture just to see it?
Yeah.
Good choice. I was gonna do it anyway, but I'm glad we can agree. So let's go 6, 2. 1, 2, 3, 4, 5, 6. 1, 2. That's gonna be our vector. Oop, almost missed that. That's vector U. And V is 5, -5. 1, 2, 3, 4, -5. 5, -5 is here. That's our vector V. So kind of hard to imagine, but we're going to look to where the perpendicular is going to be. I think. There looks like a perpendicular. So this is going to be our projection vector that we're trying to find, so we kind of have an idea. All right. How do we start again? Projection of U onto V. Start a low projection of U onto V. So, what's that magnitude, or do you want to just go, where do you tell me, where do you want to go? Home to take a nap, Grace says. That's not a choice. That was easy to read. So we need a dot product. What are we dotting?
U dot V.
U dotted with V, and that's going to be over. How do you want to do this? Do you want to do it over the magnitude squared, or you want to do it over magnitude
Let's
times
do
V?
the other one. Yeah, not
The other one?
magnitude square.
So over what magnitude?
V.
D, because we're taking out that length. Then we're going to multiply it by a unit vector in the direction of V. So V over magnitude V. Okay.
We know how to do that.
We do know how to do that. Who could forget? Let's see. Let's see. U dot V is going to be 30 minus 10. Okay. Magnitude of V is going to be square root of 50, and let's just leave it as square root of 50 and not try to simplify, because we're going to see our, we're going to multiply that by the vector V, which was 5, -5 over its magnitude, which is another square root of 50, and I see good things happening from that square root of 50 times square root of 50. We okay? Nods of heads? Okay, so, let's see, 30 minus 10, I can do that, 20. Square root of 50 times square root of 50. Suppose we could reduce that. 2/5 times our, oh, was this a carefully constructed problem or what? Man, 2/5 times 5, -5, is going to be 2, -2. Awesome.
I hope they're all like this.
I know, if only. So let's see, that was our blue. So this projection vector is supposed to, well, that kind of almost looks like it was in the right place, more or less. I mean, we're very quickly, not drawing carefully. Vector. Now we need to get this vector. Should we call this vector W? This is the vector perpendicular to our projection vector, because we want U to equal our projection vector plus W. That's, so we've done the first part here. Now we're trying to do the second part. We can do that. I like that attitude. So we're going to take our projection vector, 2, -2, plus this unknown vector we're trying to find, and that is supposed to be equal to our original vector U, which is 6, 2. I think you're right. I think we can do this. That vector that's perpendicular to our projection vector is going to be 4. Does that sound right? Yeah, I think that is right. There we go. Well done. How did you do that in one class period, guys?
Wow, with
You must be good. I think we can even try to do a practice problem or answer more questions. And you would like to see done or something like, yes,
This is what I want to see done, but with polar equations, do you text about the names of them, or we naming them?
Possibly. I don't remember, did you have to do it on the review?
No, we didn't.
Probably not, but I think I see a test in your future like in March where you're gonna have to. So if you wanna just go ahead and start running them, you might as well. Eventually, there's gonna be three kinds you have to know. The rose curves, the limasomes, and the lemma
Pretty
scale.
sure that if you're taking a test with higher function and you want to study it well in advance, that you'll do well on it. But if it's about root memorization, such as learning the names of the rose curves, doing an all-nighter will actually perform better.
So I guess the operative question there is, are we aiming for rote memory, or are we trying to learn and understand why they might have been named the way they are?
Well, I know what I mean.
I'm just putting that out there as a hypothetical. I didn't want an answer to that.
30 on the review.
30 on the root, can you tell me what that is?
Graph the polar equation R equals 4 plus 6 cosine theta.
4 plus 6 cosine theta?
Yeah.
Okay, so for the record, if you want to start your rote memorization, which I know is way early for you, Katya, that would be a limasome because it's A plus B cosine theta. And the way I think of it, because I'm not trying to rote memorize it, because I know I'm going to have to teach it again next year, so I don't need it just for today, is that for the right choice of cosine, we could make this equal that in B0. So this is going to reach the pole in B0. But this could even get bigger and we could cross over into negatives. You understand what I'm saying? If this fix was less than 4, if that was a 3, it would never be 0. It would never reach the pole. In which case we would get something that's going to be a dimpled or dented limasome. If that was exactly equal to 4, it would equal 0 but never cross into the negatives. It would be a cardioid. And ours is going to go through the pole. It's going to be a looped limasome.
I'm sorry, I'm a little confused. How did you get this?
So this was given to, so the way I'm thinking of it is, because I know cosine can be anything between -1 and +1. So for the right theta, I could make this equal 0, and in fact, I can make this be a bigger negative than 4. So this will, for some choices of theta, be positive, for some choices be 0, and even cross into the negative. Now, if this had been like a 3 instead of a 6, there would be no way this could ever be 0.
Okay.
So, because the biggest negative cosine could be as -1, and 4 minus 3 would still be positive. So it would never, so here's the pole, it would never quite reach the pole, which is going to make it a dimpled or dented limasome. If it was exactly 4, then for the right choice, this would equal 0, and it would touch the pole and be a cardioid.
And if it's greater than 4, it's
Then it's going to cross into the negative, so there's the pole. It's going to cross in and do that anyway. So then what you're going to do is you're just going to plot what is R at the quadrantal angle.
So is the key wrong?
So you're going to plot them at these points and then connect them.
So I think that my mistake is that the key's wrong because you have it on the key as a cardioid instead of a loop. Yeah. So I was really confused. I'm going to just where that it should be looped though. Because I did this part and then I was like, well,
Then you
that
did the-
yeah. I think I'm good then. Got almost everything right. So thank you.
Or,
You should never.
yeah, you should know. Those are the- I mean, you're going to have to estimate.
Copy has another rote memorization before.
I put off
never get.
Good afternoon, LHS. Next week is Picture Day. 8 group students will have your picture taken Monday, September 21st
let me run
in the
again.
afternoon. If you would like an order form, come get one from the main office and have an awesome day.
That's a test, but yeah.
Oh.
You'll be totally. Remember what stressed me out so much last year when like all the VC kids were still in the room doing whatever and we were standing out there waiting for Mr. Streeter.
Okay, let me hand out singles first,
Thank you.
and then see if we have enough left over for double, one and another.
Yeah.
I want to know.
More than that.
Oh, you didn't get one?
Do you want one?
I need to
talk to you about the test.
Okay.
Never mind.
I know you're making this.
Yep.
Okay.
Also, I was wondering, like, the next two, how many times is it March?
I don't need it. I don't want to do it.
I get those now.
Wait, I already gave mine off camera.
Oh,
Okay.
I think they're all.
Okay,
Okay.
cool, never mind.
I like coming here tomorrow morning. And I can just come after that. I'd have to go.
And when do you wanna take
Yeah.
I might have time next.
Well, I'll make a group chat with you and Colin in it.
Okay.
And if
Yeah,
you want me to
that'll
do
be
it before
good.
then I can
Awesome.
probably
Okay.
come in, like, do you have first and second family?
I have second and third this year. So I could do that on a virtual day.
If you want me to do it sooner than that, I can start sending on like Tuesday, Thursday next week.
The same for Thursday, okay, does that give you enough time? Okay.
It's mostly the imaginary that I'm getting stuff out, imaginaries and folders.
Can you come in and talk to me, or?
I start
Stan
having
or somebody?
next week.
Okay.
I might come after school, but I don't think I have time. We usually get started 15 minutes after.
Yeah. Okay.
It's Mrs. Sweet. Have a good day.
Of course it is.
Oh, wait, I gotta stand it. Hold on there, I'm running around.
Like at all, but you have to get like
Um,
a 70 something.
I've got something in mind.
What?
Yeah.
Oh, so don't fail. You know, all the fun stuff. You know, I'm just gonna fail. What kind of attitude is that, Fiona? You know, it's the same attitude for Mr. Shirley was my thing. And he's like, but Fiona, this wasn't too good. And I'm like, it hasn't been my best work, no. And he's like, everything's your best work. And I'm like, not this. But to be fair, like my husband got deleted and I got I do the last dance. It's always fun.
Sandy.
I went to a comics class, my desk is always flat. I'm like, back on it.
Yes. Point blank. I'm gonna try to get caught up on homeworks here. So I'm gonna try to answer all those once we take that test on Friday. So in a moment, I will be looking for 9, 10, and 11. 9's the review, and then 10 and 11. Okay. Let me see if I can get this video uploading real quick.